the distance r tangential to the path?
Oh, so it's basically a speed when it's not at the either apogee or the perigee, or
Well, it's the speed at any position. If I put in r for perigee here, I'll get this formula. If I put in for r at apogee, I get this formula.
Oh, so it's just like the general formula.
It's a general formula for the speed anywhere in the orbit.
Okay.
Okay. Any other questions?
Yeah. I have some questions on chapter 13.
Yeah, go ahead.
13.38. Also 13.39. They're pretty similar. I just was having a hard time with those two problems.
Okay.
Mm-hmm.
Well, the issue with these kinds of problems is usually setting up the integral correctly. So let's go ahead and set up the integral for number 38. So here is an axis. And how have they set it up? It doesn't really matter. Here is a rod of length L. So this is x equals 0. This is x equals L. I have a point mass here such that this distance I'm calling, well, I can't reuse the symbol x, can I? Let's you know, they really screw you up by calling that the distance x. We need a new symbol for along here. So Aurelio, you pick. What am I going to use as my symbol for this axis, the horizontal axis?
Z.
Z equals 0. Z equals L. And this distance here is x. Okay, now I want to know the gravitational attraction of the rod on the mass m. Well, take a little slice, dm, which is lambda dx, and df for that little slab with respect to the force on this mass here is going to be big G dm, the little m, over r squared, which is equal to G lambda dx times little m, only this is not dx, it's dz. We already went through this. So lambda dz divided by r squared. But what is r? R is this distance right here. Okay, so that would be, this is r. Now this distance right here is the distance z of this differential mass from the origin. So r is equal to x plus L minus z, and that's squared. Is that right? X plus L, then subtract this z, that's the distance. Okay, so f is just the integral of z from 0 to L. And you can do that integration, right, Aurelio? How would you do it?
Yeah, that so then we're doing the integral with respect to z, right?
It's integral with respect to z. So are you going to use substitution?
Yes, I think so.
And what will be your substitution? U equals,
U is equal to um x. Uh, I don't know.
you almost had it. I thought you were going to say it. X plus L minus Z.
Minus Z. Okay.
So then this term becomes U squared,
Mm-hmm.
and du is equal to minus dz.
Okay, and then the rest of the variables, you just bring them out front as a constant.
G lambda m. That's right. So G lambda m times du. So dz is minus du. So all we need to do is flip the signs here. Over
Yeah.
u squared. There you go. Okay, now it's trivial, right?
Yeah, that's easy.
Okay. Only it's not L to 0. We have to go by and substitute for u. If x or z is equal to L, then
X.
this is equal to x, exactly. And if z is equal to 0, then this limit here becomes x plus L. Okay.
Okay. Okay. And then I have a question. I don't know. I understand the integration, how you do that, like the math part of it, but I'm still kind of lost as to how this kind of fits in the orbital motion.
It doesn't.
Oh, it doesn't?
It doesn't. No, this has nothing to do with orbital motion. This is just the gravitational force of one object on another, determined
Okay.
by integration. In orbitology, we usually assume that the planets are spherical, so we don't have to do any integration. If I have, here's the sun, here's the center of the sun, here's the Earth, the force is between the centers, and r is the distance between the centers in the universal law of gravitation. So you can
Right.
write down the force immediately. And the issue becomes what motions are allowed. This problem from Mastering Physics, problem, I think it was 38, is nothing but how do I determine the force for an extended object using integration?
Okay. Can I just kind of just kind of speak can I just kind of like talk out loud real quick just to
Yeah. Go ahead.
So I guess what you did was let me see, where'd you get the lambda?
Well, lambda is just the density of the linear density of the rod, and lambda is going to disappear in the final answer, but you can leave it in there if you want. Lambda is equal to the total mass, capital M, divided by L. So it's the mass per unit length.
Okay.
You've seen this before because we've done the center of mass problems using the concept of a linear density, right?
Right. I think I just need to brush or touch on this again. Yeah.
All right. Is there anything else? Did you want to look at number 39? It's the same kind of thing.
No, I think I'll pass on that one, but I did have another question.
Go ahead.
It was problem 13.79. So it's a problem 13.79, part B, and specifically how I'm supposed to find the value for A, for part B. I guess in order to solve for, yeah.
Well, part B asks, how long does a one-way trip from the Earth to Mars take? Is that the part you, well, just talk about the whole thing. Let's just talk about the whole thing.
Okay.
Okay. So here you've got the orbit of the Earth. Here you've got the orbit of Mars. And of course, the sun is at the center, right? That's the sun. Well, what we want is an orbit that connects the orbit of the Earth to the orbit of Mars. That's the transfer orbit. And I'm going to try to draw it. Okay, so this red orbit is the transfer orbit. Now, we want to know about the transfer orbit. If we know the eccentricity and the semi-major axis of an ellipse, we know everything about it because it's a planar figure. So we should only have to know two things to completely characterize it. So the first thing we know is that this distance right here is r at perihelion for the transfer orbit. But that r for perihelion is the radius of the Earth's orbit. See how this connects Mars and Earth orbits together? But we know that that is equal to 1 minus e times a. Now we know that this distance right here is the radius at aphelion of the transfer orbit, but that's just the radius of Mars orbit. And that, because it's aphelion, is 1 plus e times a. Now, we know the radius of the Earth's orbit and the radius of Mars orbit. That's in the appendix in the book. That means that we have two equations in the two unknowns for A and E. And I'll tell you the solution right away. A is equal to Rm plus Re over 2. So the semi-major axis is always the average of the aphelion and perihelion distances. And E can be calculated from either of these two equations. Let's say E is equal to 1 minus Re over A. I think that's right. Yes. Okay, so now you know everything. In particular, what's part A? What direction must the rockets be fired at the Earth and at Mars? Okay, in both cases, we're going from a low energy orbit to a high energy orbit. So we fire forward, which is confusing. We fire so as to speed up. However you want to call that, we fire so as to speed up. So at this point, we have to fire the rockets to propel the spacecraft forward at a greater speed. Here, we're going from the transfer orbit to the Mars orbit, but the Mars orbit is a higher energy orbit. So we have to fire so as to speed up and go into Mars orbit. And the way they ask it is in the direction of motion or opposite to the direction of motion. So I think what they mean is, here's my spaceship. I fire that way. So my exhaust goes that way. I move the spaceship forward. I think that's what they mean. But who knows what Mastering Physics wants? Okay. Part B is, how long does the trip take one way? Well, the period of the transfer orbit is equal to 2 pi times a to the 3/2 divided by the square root of gamma. This gamma is the gamma for the sun because we're going around the sun in these orbits. A is this semi-major axis here for the red orbit. So the period is this. So how long does it take to go from here to here? The period divided by 2. So half the period of the orbit takes you to Mars, and then the other half of the period of the orbit takes you from Mars back to Earth. And what's part C? To reach Mars from Earth, the launch must be timed. Oh, okay. Part C has to do with the timing of it. Let's say that let's use another color. Let's use brown. Let's say the Earth is right here. Well, we need to fire our rocket right here such that Mars will be right here after p/2. So Mars has to be at a certain angle. Okay. So if Earth is here, then Mars needs to be right here when we fire. Because the time that it takes for the rocket to go from here to here, which is p/2, is the time that it takes Mars to go this distance. And this angle is 44 degrees. So all you have to do is figure out what is the velocity of Mars in its orbit. So I know the velocity of Mars in its orbit. And I need the speed. Let's see, the velocity of Mars in the orbit is such that I need this is equal to this distance, let's call it S, over the p/2 time. So now I know, since I know the velocity of Mars in the orbit, and I know this time from this, I know what this S is. So this S is a certain percentage of the orbital circumference, and I can figure out what that angle is right there, knowing this distance. And I think that's it. Okay, is that good, Aurelio?
Yeah, for the most part, it's good, but for A, I don't, is that the semi-major axis of like Mars? I mean,
No, this A and this E and these R's refer to the red orbit, the transfer orbit.
right. Oh yeah, yeah. Right. Okay, and then A, that would be like kind of like the radius, right? Like the semi-major axis, but like in a horizontal direction.
Yes. Excuse me, let me draw it. Here's a line that goes through the sun from one point to another. That's the center. This distance right here is A for the transfer orbit.
Okay, and oh wait, I think I understand how you got the A. So then it would be the radius of Mars plus the radius of the Earth, and then could you explain that one more time?
Well, let's solve these two equations and let's see what we get. So let's divide Rm by Re. So Rm over Re is equal to 1 plus E over 1 minus E. Is that right? Because the A's cancel. So that means R Earth. No, I'm sorry. Yeah, R Earth plus E R Earth must equal Rm minus E Rm. So let's solve this. E times Re plus Rm is equal to Rm minus Re. So the eccentricity is the difference between the two radii divided by their sum. Now let's solve for A. So A is equal to R of the Earth over 1 minus R Mars minus R Earth divided by R Earth plus R Mars. So let's go over here, get a little bit more room. Let's multiply top and bottom by Re plus Rm. So we get Re times Re plus Rm divided by Re plus Rm minus Rm plus Re. Okay, I did this in my head, but did you see how I multiplied top and bottom by this term, Re plus Rm? Well, look, the Rms cancel. The Re's cancel, except there's 2 times Re. So this becomes R Earth plus R Mars over 2. So I just showed you where this formula came from. That's just the solution of these two equations for A. And knowing that, we can solve for E. There's more than one way to solve these two equations, right? I mean, we can solve for E first or for A first.
Okay. Oh, okay. So, but there's no, just looking at it, you wouldn't be able to figure out that it's Rm plus Re over 2, right? You would have to like.
If you're really smart, you could. I just happen to know that was the answer, so I wrote it down.
Right. Okay. 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 Thank you. That I'll have to laugh.
Okay, good. Okay, other questions?
Yes, Professor, I do have one question on chapter 13, Mastering Basic.
Good.
Can we go over number 13.63?
Okay, 14.63. Okay, an object is undergoing simple harmonic motion with period 1.2 seconds.
Oh, it's actually 13.63, chapter 13.
Well, this other one is interesting too.
Oh, okay.
Okay, let's do 13.63. Okay, this is actually a rather difficult problem. So we have 2 identical stars of mass m orbit around their center of mass. Each orbit is circular and has radius r so that the two stars are always on opposite sides of the circle. So let's draw a picture of that. Now, by the way, this is not a Kepler orbit, is it? I've got two equal masses. The primary and the secondary have the same mass, and they both orbit about their common center of mass. A Kepler orbit is one body massive at the focus of an ellipse and the other body going around it. So it's not quite the same thing, but a lot of the same ideas. Okay. Okay, so here's the first star. And here's the second star. So they're always on opposite sides of the center of the circle. And they orbit their common center of mass, which is right there. So this is the center of mass. Now, let's say that they're going in this direction. Now, what do we want to know? Find the gravitational force of one star on the other. The orbital speed of each star, and how much energy is required to separate the two stars to infinity. Okay. Now you're given, what information are you given? You're given the radius of this circle is r. And for part A, we want to know the gravitational force of one star on the other. Well, that's easy to write down. F is equal to G m squared, right? Because m times n, they're both the same mass, divided by the distance between them squared, that becomes 4r squared. Okay, that's obvious, right, Truck?
Yes.
Okay. Now, for part B, the orbital speed of each star and the period of the orbit. Well, we know from way back in chapter 3 that the force F is a centripetal force, and that's equal to mv squared over r. So in order for this mass to be in uniform circular motion around this point at the center, the force towards the center must be mv squared over r. But we know what that is. That's g m squared over 4r squared. Okay, so now we solve for the velocity v. And we get v is equal to g over 4r square root. All right, is that clear?
Can you explain once again about why the force of centripetal equal to the force?
Why is the centripetal force equal to the gravitational force?
Yes.
Because the gravitational force is the centripetal force. The only thing that's acting to pull this mass towards the center is the gravitational force.
Okay.
So gravity is providing the centripetal force. And we want to know the period. Well, the period is easy. Period is going to be equal to what? Is going to be the circumference, which is 2 pi r, divided by the velocity v, right? Because if I'm traveling with this velocity, then the time it takes me to go all the way around once is just 2 pi r divided by that velocity. Now, what's part C? Oh, how much energy is required to separate the two stars to infinity? Well, that's easy. The I'm thinking about this for a second. Okay, the total orbital energy, E total, I almost said something that was wrong. The total orbital energy is the potential energy minus gm squared over 2r plus 1/2 m v squared, but there's actually two of them, so it's just plus mv squared. Okay, let's look at what this is. So this is the potential energy gravitationally between these two masses, right? Only that's not an m squared, that's an m. Oh no, it's an m squared, I'm sorry. Okay, so it's gm squared over 2r. Now, what about the kinetic energy of the system? 1/2 mv squared for each mass, so it's just mv squared. And that is equal to minus gm squared over 2r plus m times g over 4r. Oh, I forgot the m. I knew there was something wrong. There's an m here, isn't there? So I crossed out this m and the square, but I've still got m here. Okay. So that's m squared g over 4r. All right. So the total orbital energy is equal to what? Minus gm squared over 4r. Okay, so to separate these two to infinity, I have to have the gravitational attraction. I'm sorry. I have to have the total energy of the system equal to 0, which means that I need to add a delta E equal to gm squared over 4r. Okay, let me go over that last part because I don't think I was clear. For bodies in a bound system, like these two stars orbiting each other or the Earth orbiting the sun, there's a total orbital energy. Now, for a Kepler orbit, the total specific orbital energy is minus gamma over 2a. But this isn't a Kepler orbit. It's something different. So I can determine the energy of the orbit because I know that the gravitational potential energy is minus gm squared over 2r plus 1/2 mv squared for each of these. So plug in v, and I get this as my total energy of the orbit. When the total energy of the orbit is 0, they can be that is the energy such that these particles are no longer bound. So I want the total energy to Are you talking to us, Aman? Okay. That means I need to add this amount to make the total energy 0. That's the amount of energy I have to add in order for these two particles to not be bound to each other. So let's say that I don't change the energy of this one, but I change the energy of this one by this amount. Then this will fly off to infinity. And as it moves, this will try to go around it, but it won't be able to make it. So it'll go off to infinity like this. So we get a motion that looks something like that. But they will eventually become infinitely far from one another, and they will never form a closed orbit if I add this amount of energy. Okay, was this your problem, Trook?
Yeah, it was the last part, but thank you.
Okay, so the last part was the one that was confusing.
Yeah.
So the principle is the total orbital energy is negative for a bound system. For an unbound system, it's either 0 or positive. So the minimum amount of energy that I need to add makes the orbital energy of this system 0. Okay, good. Other questions? No other questions? What about chapter 14?
Professor,
Yes,
I actually have one concern.
go ahead.
I think it's just only me, but like we have a lot of assignment due tonight. Like RV, MP, and PIP, and then we also have a lab report from last week. Is there any way possible that you can extend the deadline for MP chapter 14 to tomorrow?
Let's see what we can do. Okay, we have PIP chapters 10 and 11 are due December 6th. Let's edit. I don't understand this. Okay, let's just open it up. So the 11th is what, well, the 8th is your final, right? The 8th is your final. The 11th is Saturday. Okay, I'll give you till Saturday. Okay, so you can have till Saturday for this. So if you still need to work on it after the exam and hand it in, you can. And you can, if you want to, you can resubmit. So let's go back to assignments and see what else we got. We have the moment of inertia lab is due on Wednesday. You know, I didn't make the other class do a lab report for this because they ran out of time. I'm going to eliminate this and say that you don't have to do a lab report. I kept a record of everybody that was present and worked on the lab, and I went around and talked to you. So I'm confident you understand it. So I'm just going to give you credit if you showed up. How's that?
That sounds great.
Thank you, Professor.
Okay, now let's go to mastering physics.
Professor,
Yes.
if we turned it in, could we get extra credit?
No, sorry.
Okay.
But
And then
I'm proud of you that you did it in plenty of time and turned it in. Good job.
Thank you. Will the final be in person?
No. The final will be online. It'll be in Canvas, and you'll just upload it to Canvas.
Okay, and then you said we can, or correct me if I'm wrong, but did you say we can use our notes?
Oh, it'll be open note, open book.
Okay.
Yes, just like the midterms.
Okay.
So let's see, this is you guys. Okay. So chapter 11 is due today. Boy, I gave you a lot of time on that. That should actually have already been done. But let's make this due on the 8th. No, what the hell with it? Let's just do it Saturday. That's fine. So you can go and backfill any of your mastering physics up until the 11th. And after that, I'm gonna look at it on the morning of the 12th and assign your grade. Even though it says it's available until the 22nd, it won't be available past the 11th because I'll assign your grade on the 12th. Okay, is that good? Does that help, Truk?
That helps a lot, Professor. Thank you.
Okay, how do I get out of here? Okay, good. All right. Other things. Now there must be chapter 14 questions because we haven't talked about chapter 14 M and MP at all. All right. Well, I'm going to make an executive decision here. There is a handout called Simple Harmonic Motion in a Nutshell. We have discussed simple harmonic motion, but not damped or forced harmonic motion. I don't think we have time to go over that material, and even if we did, it would be pointless. So let's look at the problems assigned in chapter 14 and review them as our review for simple harmonic motion. And I won't include any questions on the final exam having to do with damped and forced motion. Okay. Is that okay?
Yeah, perfect. Thank you.
All right. Now there's a pip problem having to do with Q of an oscillator. That's damped forced motion. So just ignore that particular pip problem. And just hand in the other one. Okay, chapter 14. I'm just going to review all of these. That's the best way I know of to review the material. So let's just go over all of them, at least to some level of detail. Okay. So problem 14.40. What have we got? A thin metal disc with a given mass and a given radius is attached at its center to a long fiber. The disc, when twisted and released, oscillates with a period of 1 second. Find the torsion constant of the fiber. I don't know if I defined torsion constant for you or not, but it's very similar to Hooke's law. F equals Kx. The torque is equal to kappa, which is like a little k, times theta. So if we write down the equation of motion for something undergoing rotation because of the torque on a fiber, we can write tau equals I alpha. And tau is equal to, it's actually minus k theta because it's a restoring force. So minus kappa theta is equal to I times d squared theta dt squared. So my equation of motion becomes d squared theta dt squared equals, plus kappa over I theta equals 0. Okay, now for a mass on a spring, we have d squared x dt squared plus k over m x equals 0. And the angular frequency is the square root of k over m. What is the angular frequency here? Aman, what's the angular frequency for this equation right here? What is the angular frequency for this motion right here? And I gave you a clue by writing this down. That's exactly right. It's a kappa, but k is fine. The square root is for both. Yes, that's exactly correct. Simple harmonic motion is always d squared x or theta or whatever it is, dt squared plus omega squared x equals 0. And this is the form of the equation. So this x could be a theta or a y or a z or anything at all. Okay, so if I know omega, which it tells me f, and omega is equal to 2 pi f. If I know omega and I know I, then I know kappa, but it's a disk, so I is 1/2 mr squared. Okay, does anybody have any questions on this? What this was an exercise in is recognizing that the equation of simple harmonic motion is of this form, and oh, if it's of this form, then omega squared must be kappa over I. And then you got everything. Okay, good. Number 53. Oh, two pendulums. A solid ball of mass m supported by a massless rod. But the ball for pendulum A is tiny, whereas the ball for pendulum B is much larger. Ah. Find the period of each pendulum for small displacements. And which one takes longer? Okay. Well, for pendulum A, which looks like this, omega is equal to square root of G over L for a simple pendulum. So square root of G over L is 2 pi F, but F is equal to 1 over T. So that means that the period T is 2 pi times the square root of L over G. Now for pendulum B, we have this situation. This length here is L over 2. And this length here is L over 2. So now we have to write down the equation for omega for a physical pendulum. So let's do that. It's a little bit complicated. So for a physical pendulum, omega is mgh over the rotational inertia square root. Now this h is the distance from the pivot point to the center of mass. So that h is L. And what is I? Well, I is equal to I, center of mass, plus m, I need a symbol here. Let's just say r squared. So rotated about the center of mass here, the rotational inertia of the sphere is 2/5 m r squared. But I translate the axis using the parallel axis theorem to right here. That becomes plus m, and I wrote r there, and that was a bad choice. Let's call it md squared, where d is the distance from the center of mass to the axis. That becomes L squared, but R is equal to L on 2. So this becomes L squared on 4. So this equals 2 mL squared over 20 plus mL squared. So this becomes what? 1.1 mL squared. So this omega is mgl divided by 1.1 mL squared. So the m's cancel, the square cancels, and the period for pendulum B is equal to 2 pi times the square root of 1.1 L over G. So which one has the greater period, A or B? What do you think, Andreas?
I would have to go with B.
Yeah, sure. B has the greater period, obviously. Not much greater, but greater. Okay. Look at 58. Oh. Okay, 58 we're not going to do because that has to do with damped motion. So let's leave that and come back to it if we have time. 64. You know what? We're going to have to talk about forced motion a little bit. So let's consider, think about your little brother on a swing, okay? And you push him to make him oscillate like a pendulum. If you push him at the right time, the amplitude of his oscillation will increase. And if you push him at the wrong time, his amplitude will decrease. So let's say we give him, he goes up, he comes back, and we push him when he's at the top. Then he goes higher. Then we push him again, and he goes higher. Okay. So the frequency with which you do your pushing will determine the amplitude of the motion of the swing. And when the motion, the amplitude of the motion is maximum, when the amplitude is maximum, that is called resonance. So let's say we have x of t equals a cosine omega t plus some phase angle. So this is basically simple harmonic motion, except that I put a phase angle in right there. Now, it turns out this omega is not the natural frequency. This is the driving frequency. So the driving frequency will determine how big A can become. I'm trying to think of another example for you. Well, let's use the swing example again, only I'm going to change it. Let's hang a bowling ball from the ceiling. And I'm going to take a little piece of paper that I fold up to make it a little bit rigid, but not very. And I hit it. It'll move a tiny bit. But if I hit it again at the right time, it'll move a little bit more. Eventually, I can make this bowling ball do this just by tapping it with that newspaper. But what would happen if I tap it and then I wait a long time? Then I tap it, then I wait a long time, then I tap it, then I wait a long time. I'm not going to get this buildup, am I? So what I'm going to have is an amplitude versus driving frequency. The amplitude is very small if the frequency is small, if the period between taps is large. And what happens if I go tap, 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 like that? Well, equally, the amplitude of the bowling ball is not going to become very large for the same kind of reason, which is I start it moving, but then I hit it immediately. And then I hit it again, then I hit it again, then I hit it again. Very rapidly, in rapid succession, okay? I'm not going to make this bowling ball have a very big amplitude. So what's going to happen is that at low frequency, I get a small amplitude. At large frequencies, I get a very small amplitude. And somewhere in the middle, I get the maximum amplitude. That is the resonant frequency. And the resonant frequency is about equal to the natural frequency if the damping is not too great. And what do I mean by the natural frequency? Well, the natural frequency of this pendulum is the square root of G over L. So that natural frequency is the frequency that appears here, the omega in this equation. If I have a driving frequency, I have a term over here on this side that's non-zero. And eventually what will happen when I drive this oscillator is that the natural frequency will disappear and the motion will become steady state at the forcing frequency or the driving frequency. And if that driving frequency is about equal to the natural frequency, then I get my maximum amplitude. That's what is meant by resonance. So in this problem, which is problem 64, we have 4 people compress the springs of a car by 4 centimeters when they get in. So here's the car, and here are the wheels, and there's shock absorbers for each of these wheels. And let's say there's 4 of them. Well, these shock absorbers are like springs with a spring constant K. And F is equal to Kx. So if I depress the car 4 centimeters, and the force is 4 times, or rather the mass of all the passengers, which is 250 kilogram times G, then K for those springs must be equal to 250 times G divided by 4 centimeters. So my K, did I do that right? Yes. So K is 6.13 times 10 to the 4 newtons per meter. Okay, now what's the rest of the problem? If the car has a period of vibration of 1.92 seconds, what is the period of vibration of the empty car? Okay, so we have 4 of these Ks in parallel, right? That means that the K effective is 4K. And we know the period, omega, is equal to square root of K over M equals 2 pi over the period. So that means the period is equal to 2 pi times the square root of M over K. And this M is the mass of the passengers plus the mass of the empty car. So you know the period is 1.92 seconds. You know the mass of the passengers is 250 kilograms. You can solve this for the mass of the car. So now you know the mass of the car. Now, what's the period of vibration of the empty car? Well, that T for the empty car is 2 pi square root of M of the car over K. So the first part of the problem you use to solve for the mass of the empty car. Now you know the mass of the empty car, you know what the natural period of vibration is. Okay, are there any questions on that? All right. You didn't need to know the concept of resonance for this. You just needed to know that the natural frequency was the square root of K over M. This problem has changed. In the other edition, in edition 14, the problem is that there's a washboarded road that looks like this, right? There's washboards in the road, and these washboards are some distance apart. And if you go at a certain speed, the bouncing up and down is maximum. What does the bouncing up and down mean? That means resonance. So you hit one of these bumps at a certain speed, that tells you what the resonant frequency is. Because the time, 1 over the time between bumps, is the frequency. So that tells you the resonant frequency. And now you make the association, resonant frequency is almost the same as natural frequency, and solve the rest of the problem. Okay, is that clear? Is that good? Any questions? All right, let's look at number 66. So we have a block on a frictionless surface, I think. Yes, it is. And there's a spring connected to this mass, which is big M. And then there's a little m on top of it, and the coefficient of friction, mu, between these is a maximum mu sub s that's presumably given. What is the maximum amplitude of oscillation such that the top block will not slip on the bottom block? Well, let's think about what's happening. If I pull the big block M a distance here, so that that is the amplitude, then there will be an acceleration of this block and the block on top of it, which is equal to what? Well, the force is going to be K times A. Therefore, the acceleration of these two blocks is equal to K A over M. Only it's little m plus big M, because it's the total mass. I'm assuming these two are stuck together because of friction. Now what we want to do is, given this acceleration, what is the frictional force between the blocks? Well, let's see. We have, for the little block, we have the force of friction is acting this way. Is that right? If the whole system moves this way, then the frictional force must act in this direction to keep this from sliding off. So we have on little m, we have a frictional force right here. And that frictional force must equal little m times the acceleration, Ka little m plus big M. Now we know the maximum frictional force is going to be mu s max times little m times g. So these m's cancel, and the maximum amplitude that I can have is going to be mu s g times little m plus big M over K. Because my maximum acceleration, and therefore my maximum frictional force, is going to occur when the force is maximum, which is going to be right here at the maximum amplitude. Okay, does anyone have any questions on this problem? All right, let's go to another one. Number 72. let's skip that one for a moment and go to 83. Okay. So here is a spring attached to a mass. It's a frictionless surface. And we have a bullet with speed v. So we have the mass of the bullet, little m, and we have the mass of the block, big M. This bullet embeds itself into the block. And after that point, then the mass undergoes simple harmonic motion. Okay, so what is it they actually want to know? The impact compresses the spring a maximum distance of 15 centimeters. Oh, that just tells you what K is. Okay. So after the bullet strikes this mass, it compresses a maximum distance here. Let's call this D. Well, we're going to use conservation of momentum to determine the initial velocity of this mass at the end of the spring. So conservation of momentum tells me little mv must equal little m plus big M, and I'm going to call this V1. V1. So V1 is equal to the mass of the bullet times V, the mass of the bullet, plus the mass of the block. Now, at this point, the collision is over, so I can use conservation of total mechanical energy. So I have this velocity, so my total energy is going to be 1/2 m times V1 squared. That has to equal the total energy of the system when it's compressed its maximum amount D, which is just 1/2 K D squared. Okay, that means that I know, since I know V1, I know K. So K is known. So if I know K and I know M of the system, I know the frequency of the motion is the square root of K over M. Or F, oh, that's little m plus big M. So F is just omega over 2 pi. They probably want F, not omega. Okay, does everyone see the point here? We use conservation of momentum to see what V1 is. We know V1, we use conservation of mechanical energy because we know D to find K. Now that we know K, we know the angular frequency, and the frequency is just the angular frequency divided by 2 pi. Does anybody have any questions on this one? All right. Okay. So in problem 85, we have a ball at the end of a string and another one here with the same L, and you're given this distance D right here. Now the upper ball collides with the lower ball and sticks to it. The strings are both 50 centimeters long. These two have different masses. So we have mass 1 and mass 2. These are different masses, but L is the same. So these two balls stick together. And we want the frequency and maximum angular displacement of the motion after the collision. Well, what is going to be the speed of M2 just as M2 hits the first ball? Well, that's going to be given by conservation of energy. We're going to have M2 GD equals 1/2 M2 V2 squared. So V2 is equal to the square root of 2GD, which we've seen I don't even know how many times. Now the two of them stick together. And the new composite mass, big M, is equal to M1 plus M2. Well, the frequency of the motion is easy to find because it doesn't depend on the mass, does it? Omega is equal to the square root of G over L. So you know what L is, and you know omega. Now, the second part of this was the maximum angular displacement of the motion after the collision. Well, the maximum angular displacement will look like this. Here are the two balls together, capital M, at an angle theta, and a height here equal to h. So we're going to have 1/2 capital M, which is M1 plus M2, times V2 squared must equal big M G H. Well, the M's cancel, and the height H is going to be given by V2 squared over 2G. Okay. Now, look at the geometry here. This height is a height H. This distance right here is L minus H. That means the cosine of theta is equal to L minus H over L. And we'll write that as cosine theta equals 1 minus H over L. Okay, now you can figure out what theta is just by taking the arc cosine. Interestingly enough, the masses of these balls don't enter into the answer of this problem at all. Oh, no, wait a moment, I'm wrong. I think I made a mistake. Let's go over this again. Of course, the masses enter into it. They have to. Okay, so up to here is correct. Now we want to find V3. V3 is the speed that the composite mass moves off at. Okay. So now we have M2 V2 equals M1 plus M2 V3. So V3 is equal to M2 divided by the composite mass times V2. Okay, now it's V3 that determines how high I go. So I have 1/2 the composite mass V3 squared equals the composite mass GH. And now we have H equals V3 squared over 2G. Okay, my mistake was to use V2 instead of V3 here for the composite mass. Okay, is everybody good with this? Okay. So how do you want to proceed from this point? I think we've done enough problems to give you an idea to cover most of our material. Does anybody have any questions or anything they want to say? All right. I actually think this is a good place to end the semester. I'm sorry it ended with such a whimper.
Professor, I have a question regarding my quiz grade from a while back.
Which quiz?
It was the last one we took.
Quiz number 4? Okay, and Chris, right?
Yeah.
Yes, you asked me to check that. And I did, but I didn't write the number down, so I'm gonna have to, I didn't put it in mastering physics. Okay, what was the problem? The problem was that one of the pages was missing?
Yeah, I emailed it to you and it's in
And I
Canvas
got
too.
that. I
Okay.
got that. And the answer is you obviously got more than 6.
Yeah.
I've got your full test. I'll regrade it.
Okay, thank you.
All right, you're welcome. Anybody else have anything?
Professor, I have a question about regarding my labs.
Yeah.
So my first couple or 3 labs, I wrote them by hand, and on my first one, you said to submit it as typed up, and I did, but it came out 0.
Oh,
Am
I
I
just
able-
didn't change. I didn't change the grade within Canvas.
But did you want me to turn them all in and typed up?
Yes.
Okay, and I won't lose any points, right?
No, I told you could resubmit them.
Okay, perfect. Thank you.
Okay. Yeah. Just resubmit them. Okay, anybody else? Excuse me. Okay, then I think you should go study. Work M&P and PIP. Look at the old quiz problems. Make sure you understand the concepts. The important thing to understand is the concept, not just techniques for solving problems. Because if you understand the concept, then you can do any problem. I've said that before. So does anybody else have anything they want to say? Okay, well, this was a hard semester. And hopefully next semester will be a lot better. I'm teaching 2 sections of 222 next semester, so I hope I see some of you then. And I wish you good luck on your finals.
Thank you. It was a pleasure.
Thank you, Professor.
Okay,
Thank you, Professor.
all right, see you next semester.